Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Kobe and I chat with guest Jens Groth, Director of Research and Formal Security at DFINITY, previously a professor at the Department of Computer Science, UCL. Jens Groth is a leading ZK researcher and is the person behind a number of advances in the field. We chat about his earlier career, the cryptographic problems he tackled in his research, how he solved these, the results of this work, as well as his move from research into industry and what he works on today. Before we kick off, I just want to highlight the ZK link tree. There you can find links to all of our channels, including the ZK Jobs Board, the ZK Community Board, and also the ZK Hack Discord. If you're looking to learn more about ZK tech, keep an eye on that space. We have a lot of really cool things coming this summer as well as into the fall. So if you're looking to jump in, this might be a great place to start. I've added the link in the show notes. Hope to see you in our channels. Now, I want to invite Tanya to share a little bit about this week's sponsor.
Today's episode is sponsored by Anoma. Anoma is a set of protocols that enable self-sovereign coordination. Their unique architecture facilitates efficiently the simplest forms of economic coordination, such as two parties transferring an asset to each other, as well as more sophisticated ones like an asset-agnostic bartering system, involving multiple parties without direct coincidence of wants, or even more complex ones such as N-party, collective commitments to solve multipolar traps, where an interaction can be performed with an adjustable zero-knowledge privacy. Anoma's first fractal instance, Namada, is planned for later in 2022, and it focuses on enabling shielded transfers for any assets with a few-second transaction latency and near zero fees. Visit anoma.net for more information. So thanks again, Anoma. Now here is Anna and Kobe's interview with Jens Groth.
Today, I'm very excited to introduce our guest, Jens Groth. He's the Director of Research and Formal Security at DFINITY. He's previously a professor at the Department of Computer Science at UCL. Welcome to the show, Jens.
Thanks, Anna. Very nice to be here.
For today's episode, Kobe is also joining me as a co-host. Hi, Kobe.
Hello.
So I think before we start in, I want to talk about your name, Jens, because I think a lot of people will be very familiar with the work that you've done, but maybe not the way that I just pronounced your last name. We just recently learned on an episode that we have been pronouncing your name wrong all of these years. The term that we're familiar with would be Groth 16, a very important proving system that's used by many projects. But we just learned that it's actually pronounced Groth, and maybe even like Groth 16. That's how I've started to use it since then. But I want to ask you what you make of this.
Yeah. I'm also mispronouncing my own name, right? So I'm I'm Danish, so my name is Jens Groth. But especially in English speakers find that very difficult to pronounce, and I've given up, right? And I just say Groth as well whenever I talk about my own works. So I guess that's like I still pronounce my own name when I just introduce myself as Groth, but when I refer to my scientific works, I tend to say Groth, just so everybody's on the same page.
Everyone can say it. I think it's really important for our community to know that we've been saying it wrong. I can't now, and because Mary actually says Groth when she pronounces it, now I do as well. So
I'm still practicing.
But anyway, cool. So why don't we hear a little bit more about you and your background? What led you also to this really important work? I'm very excited to dig in.
So it started at the University of Aarhus when I was an undergraduate student. I was studying maths, and I kind of got a little fed up with the abstraction that was there, and I wanted to do something applied, and cryptography was sort of an opportunity to do applied maths. So I took some courses in cryptography. I really liked it. I decided to write my master thesis in cryptography, and that's sort of how I got into cryptography.
Nice. What was the main topic in cryptography at that time? What were people excited about or worried about?
Yeah, I think
I think I've seen a lot of your early work was actually around voting in cryptography, right?
Right, yeah. So after my master thesis, I sort of got into doing an industrial PhD. So I was working with a company, Cryptomathic, and they had a project on voting. So that's sort of how I got started on doing research. And in voting at that time, it would take a lot of time, actually. So there are these voting systems, and you have to, they're very good at tallying up votes. They're based on homomorphic encryption. So you can sort of like submit your votes in an encrypted form, right? So they're kept private, and you can tally them up, and you can use a threshold decryption to get out the result of the election, right? But when you do that, there's nothing that prevents a voter from submitting, 1,000 votes on a candidate, right? And that's essentially stuffing the ballot box. So you want to prevent that. And in order to prevent that, you can ask the voter to submit a zero-knowledge proof together with the vote that they have voted basically in a valid way, right? So it doesn't review which candidate they voted for, but it does ensure that they can only submit a valid vote. And at that time, that was a process. I mean, if you had like a large election with a lot of candidates, right, then that could take up to minutes on a browser at that time, right, to create that vote and submit it, right? So the bottleneck was really the zero-knowledge proof, and especially the time it took to prove that you have submitted a correct vote. So I kind of got into zero-knowledge proofs because I wanted to optimize that step for the voter.
Was zero-knowledge proofs at the time that you were doing it, were they a key topic in generally, like in cryptography, or was the focus on something else at that time?
I feel it's always been a key topic from an academic perspective, right? People have been interested in zero-knowledge proofs. And I think you also have like concrete things people do with zero-knowledge proof, like Schnorr signatures is essentially a zero-knowledge proof, right? So it's also something that has really, a practical dimension to it. I'm not sure it was so like the hottest topic at that time, right? So at that time, it was so like a few years after Kramer-Shoup encryption came out, right? So until then, you didn't really have like efficient, provable, chosen ciphertext attack secure encryption, right? And that was a big result at that time. And actually something I wrote my master thesis on chosen ciphertext attack security.
Was post-quantum an issue then? Were people already sort of looking to the future as something to work on or think about?
I think not that I recall. I mean, basically, most of my cryptographic career, I've just been working with number theoretic-based primitives, right? And not really been thinking much about post-quantum security. So I think that's some awareness that, I mean, it may have been so like in the background. I know that people were doing so like both quantum cryptography and post-quantum secure cryptography also back then, right? But it was certainly much less of an issue.
I think like maybe if we're going back to the topic of the zero-knowledge proofs in that era, maybe it's also fair to say that at that time, zero-knowledge proofs that were created were for very specific use cases. So if you look at voting, it would be for something extremely concrete and small and very different from what we have today for, let's say, generic programs. So
right, yeah.
At least I think that was even less looked at back then. Is that correct?
So there has been works that looked at also at generic programs, right? So not so much programs, right? I mean, the model has typically been that you have a circuit, right? Either a Boolean circuit or maybe an arithmetic circuit, right? If you were really fancy, right? And people did not think much about like how to translate, say, a program execution into a circuit and the cost involved in that, right? So that was sort of like the model because it's NP complete, right? And it's, I think at least for arithmetic circuits, it also relates somewhat to cryptographic operations you could do in cyclic groups, right? It made sense, right? So there were papers that sort of like did general proofs that, said you could prove that an arithmetic circuit is satisfied, right? And that sort of like got that down to sort of like a linear number of group operation in cost.
Going back to your story, so you kind of talked about like some of this initial work, which was in ZK, which was very early. It seems like it was quite early in the field. Were there many ZK researchers at that point?
I don't think there were people that would really identify as purely ZK researchers, right?
Okay.
It was more like something you would pick up along with other things that you were doing.
Interesting. But what was your next step after that? So where did you kind of go after that initial project?
So I did quite a lot of work on zero knowledge proofs in voting, right? So there's both the paradigm of doing voting based on homomorphic encryption and telling encrypted ballots. So I had several papers that optimized that and also sort of used different techniques that also like typically based on groups with a hidden order. So you can sort of like also do some integer proofs around that. There were some nice papers by Helga Littmer that sort of like initiated that kind of direction and sort of like used sort of very clever tricks with, Lagrange four-square theorem and sort of like prime visibility and things to prove that you had something that was in a particular set. So that was sort of one area I was exploring. And then there's another voting paradigm based on mixnets. So that could be used both for voting, but also for anonymous communication. So I also started looking at mixnets and did quite a lot of work in that area. And then I had sort of like some strategic thinking about like I was thinking, well, I'm good at zero knowledge proofs, where else can I use that? So I also did some work on group signatures because they also rely on zero knowledge proofs to sort of like glue everything together. So that was sort of the early days of working with zero knowledge, which always sort of like application driven, right? That there was some direct application I had in mind when I was trying to optimize it. I always liked optimizing things. A lot of this was like squeezing out the last piece of performance in these zero knowledge proofs. And then after that, after my PhD, I went to do a postdoc at UCLA. That's sort of where working with Raphael Ostrowski and Amit Sahai that I got into sort of like using pairings for zero knowledge proofs.
If we're talking about mixnets and the techniques that are used in both mixnets and voting, there is this topic of shuffle arguments, right?
Yeah.
So maybe it would be nice to describe what it is and what difference have you made there?
So the idea is that you have a bunch of people, they want to say publish some message, but they want to be anonymous, right? So you have some servers that will help them, and the idea is that everybody encrypts their message, sends that to the first server. The server then picks a random permutations and so like permutes these ciphertext. And if you use, for instance, an encryption scheme that's homomorphic, then the server can also re-randomize those ciphertexts. So you cannot sort of like see from the input ciphertext which ones match the output ciphertext, right? So now this server sends out a bunch of ciphertext that have these encrypted messages, right? But nobody can anymore see that connection. And you could pass that through multiple servers in sequence, right? To make sure that even if one of the servers is so like curious about who submitted which message, then it doesn't know either because some other server also put in a random permutation. And it's clear that, if the servers can do anything, then they might not re-randomize at all, right? They could do something else. They could substitute in new ciphertexts. They could also try to sort of like somehow mark the message so they can later see who was it that submitted it, right? So there you want, again, some sort of check that the server is actually acting honestly. That check can be then done with zero knowledge proofs. So the idea is then that each server will not only do the permutation and the re-encryption of the ciphertext, so that what is called a shuffle, right? But it will also prove that it has done a correct shuffle.
Yeah. And I think that one of the works that were pretty influential in that respect was with Stephanie Bayer, right? That you had a zero knowledge argument for correctness of a shuffle. And I think it's still quite being used today, right? Like it's also maybe one of the basis of existing general zero knowledge schemes today, right?
Yeah. So Stephanie was the first PhD student I had, right? And we were working on mixnets among other things. And indeed, we had this paper. And what was nice about that paper was, it's sort of like optimized several things, right? So it had sort of like a reasonable prover complexity, it has a reasonable verify complexity, right? But then it was also sublinear in communication. So it was a square root cost so basically what it means is that, if you think, you have to communicate the shuffle anyway, right? You have to say these are the new output ciphertext, right? So if you have n ciphertext, right, then when you make a shuffle, you output n new ciphertext, right? But then the proof can be much smaller than that, right? So in terms of communication, you're saying that, there's no cost at all, essentially, for the zero knowledge proof and communicating that, right? The cost is borne mainly by just the shuffle itself, which is unavoidable.
That first PhD student and that work, was that when you were at UCLA still?
So that was at UCL. I was not, as a postdoc, you're not directly permitted to advise PhD students, and you don't have sufficient time to do that either. But I was working with some of Amit's and Rafi's students at UCLA.
But let's talk about that move over to UCL. You became a professor at UCL. What made you choose to do it there?
Oh, so that was sort of for family reasons. So we wanted to move to Europe. We wanted to be in an English-speaking country, and I knew some of the people at UCL. So that's sort of how that got set up.
Was that already a center for this kind of work? I know that Leuven is a center for cryptography and stuff, but UCL, I now know a few people that are there, but was it already the case at the time?
So there were some good cryptographers at UCL. So at that time, it was Helge Littner, Niklas Couture, and Ivo Desmet that were cryptographers there. It's sort of changed over time who's in the group, right? So and it should be said that at that time, it was also outside of London. The idea was that UCL wanted to do industrial collaboration with British Telecom, which had a research center in Ipswich. So it was a little also remote from the university. And eventually the university found out that that was not the right strategy and moved all of us back to London.
Okay. Well, let's talk about the work that you did while you were there. This is the work that sort of leads to some of the most famous work that a lot of people in our space are very familiar with. What were the topics that you started in on there? We know that at some point trusted setups became a big theme, but where was your starting point on that sort of line of research?
Right. I think for all research, right, you have to think that it doesn't really depend that much on the institution. It's more a lot of it takes a long time to, come to fruition and have some ideas in the back of your head, right? So I do think of this as a continuous process from, as a PhD student, I was thinking about zero knowledge proof. I came to UCLA. I started thinking about some different types of zero knowledge proofs with people there, right? I came to UCL, and there was still some of those ideas that were coming to fruition. So one example of that, I guess. So the first pairing-based SNARK, right, which got us sublinear communication complexity, so you could get down to constant number of group elements to prove a statement, right, was something that I published in 2010, I think. But it was something that I already had some ideas of for that early on while I was at UCLA, right? So it's work that came from there and then was published while I was at UCL.
And where does the work with Amit Sahai come in? That was something that I often see as a celebrated topic, and the proving system for bilinear equations. And what was that about? I remember reading that it was created because general NP computations seem to be too expensive. So what was done here?
Right. So it started with a paper I had with Amit Sahai and Rafał Ostrowski, which was essentially doing non-interactive zero-knowledge proofs based on pairings. In this case, it was over groups of composite order, right? And I see that as the starting point that realized you could use Bonego and Nissim encryption techniques and use ideas from that paper to build non-interactive zero-knowledge proofs, right? The pairing sort of like gives you a multiplication in the exponent, and that sort of like allows you to do general proofs. And at that point, we were really thinking about Boolean circuit satisfiability, right? And you get sort of like a linear number of group elements per gate in that Boolean circuit. And then it's sort of like natural when you have those kind of problems, you think about, okay, how can I extend that? How can I generalize that, right? So one direction was, okay, can you do this over prime order groups, right? And it turned out that you could do that, right? And that was also driven by a question of, so we know that you cannot do just like non-interactive zero-knowledge proofs without any sort of setup. You need something that sort of like allows you to simulate, but you can actually do that for non-interactive witness indistinguishability, right? So if you give a weaker privacy guarantee, then you can do that. And for that, you couldn't really use composite order groups, right? Because then somebody needs to know the factorization and then things break down. So that was also a motivation for using prime order groups. So that was sort of like a next step, right? And then after that, it was sort of like a question, okay, but if you want to apply this in practice, right, then maybe you don't want to go through an NP complete reduction, right, of whatever you're trying to prove, because that's expensive, right? So it was sort of natural to think about, okay, but what if we have something more concrete? So there were a couple of papers there. So I had one paper in AsiaCrypt where I looked at group signatures again, right? And so like both gave sort of like general result, also applied to group signatures. That sort of like started this question of, okay, can you do, instead of looking at, say, arithmetic circuits or Boolean circuits, can you define a language over pairings that sort of is natural to both for what cryptographers would want to build and also something that you can prove things about, right? So that came out of that. And then that was something together with Hamid Sehai that sort of like did a lot of improvements on and really got the performance, because that was sort of like a very heavy construction that had, hundreds of group elements, right? And we sort of like then really boiled it down to what is the core and the essence, right? And there were a couple of related works. I also had some discussions with Brent Waters. So Brent Waters and Xavier Boyen also at the same time also realized that, these kind of proofs sort of like naturally speak this group language. And they also have some nice non-interactive zero-knowledge proofs that they used in the context of group signatures.
Do you still see use for this now that we have these more generic proving systems, or do you think it's already a bit obsolete? What's your thought about it?
I think there are still applications of that. I think people are using it. So I think there's a general question, right, when we talk about zero-knowledge proofs, which is, are you talking about small statements or big statements, right? Because, so all these things about getting sublinear complexity and really squeezing out every piece of performance is something that makes sense when you have a big complex statement, right? Then you want to get that, right? But if you have something which is small, right, then, it may not be that big a deal that you pay in a few extra group elements, right? And the nice thing about these proofs is that they are in the standard model, right? You don't have to make assumptions about, knowledge extractors and things like that. So I think there are people that appreciate that and think of these earlier proofs as sort of like being more reliable or trustworthy because they just use standard assumptions about pairings.
So I know that we want to speak about kind of what led to the kind of one of your most famous works, the Groth 16 paper. But was there anything kind of in the lead up that you think listeners should know about to understand some context to how that came to be?
Yeah, so I think I can think of two pieces of context that I think are very interesting, right? So one is that there's been sort of two tracks of work. One is based on non-interactive proofs based on pairings, and another track is sort of like interactive proofs based on the discrete logarithm problem. And there's been some sort of like interplay in my mind about, porting techniques from one side to the other and so forth, right? So I think that is perhaps an interesting point. I think that another interesting point is I really like the paper I had at AsiaCrypt that sort of introduced these succinct pairing-based arguments to start with. And I thought of that as sort of like a big scientific breakthrough. It was actually rejected several times. So people didn't like it as much. So there's a bit of interesting gossip, I guess one could do about that. But I think, I think less of Groth 16, right? I mean, it's been picked a lot of in industry. It's had a lot of applications, right? But from a scientific perspective, right, you already had Pinocchio for sort of like shaving off the group elements. And from a scientific perspective, I think the interesting thing was also I also started thinking about lower bounds and, how good is this? Is this optimal or not, right? And actually, the title is so on the size of non-interactive zero knowledge proof, right? And of course, I think there's this distinction between what does a scientist find interesting in a paper, right? And what does an engineer find interesting about a paper, right? And those are somewhat distinct notions, right?
What you're sort of saying is a lot of the pieces had been prepared in advance. And would you say that this was just the formalization in a way that was easier for an engineer to be able to use? Or were there advances in that work as well?
So there was this nice line of work, right, by Gennaro Gentry, Pano and Rykova in 2013, and then Pinocchio by Pano, Hall, Gentry and Rykova also in 2013, right, where they actually gave concrete pairing-based SNARKs, right, that were succinct. And it was I was reading that and I wanted to understand it, right, and I want to optimize it and see if I could get something more out of that, right? So that's the concrete background of why I did that. And they introduced some really nice things. And I think one thing, there was a little back and forth discussion about that. I was one of the reviewers of that paper, so I guess it's okay that I reveal my anonymity many years afterwards, right? And maybe they thought of me as a reviewer too, the one that always gives these horrible comments, right?
Yeah.
But some of the discussion was that, so in this, the first SNARK I had proposed in 2010, and also Helga Littmer had some ideas for more efficient SNARKs, and those were universal in the sense you could take any circuit, any arithmetic circuit, right? And then you could have the inputs, and then you could prove things about that. And what came up in the GDPR paper was the idea that, if we fix the circuit, right, then we can actually do something more efficient, right? And they had introduced the idea of quadratic span programs, and also in the appendix they had the ideas of quadratic arithmetic programs, right? So there was a bit of a discussion back and forth, right? Are you comparing apples to oranges because this is not universal, right? This is just for a fixed circuit, right? But of course you can have universal circuits, and then you pay an overhead, and then you give it a proof. So there was a little bit of discussion back and forth, and also a bit of confusion about that point, right? But I think in the end it's been a super fruitful piece of work they had, right? I mean, they introduced the idea of quadratic span program and quadratic arithmetic programs, right? And I think that was a really good idea, right? Because they did get much better efficiency because they specialized to a specific circuit.
I think this discussion around universality is still happening, but maybe in a different level today with the introduction of, let's say, you have circuits, but you also have circuits that implement zero-knowledge virtual machines and all that. So it's still happening, but in a more complex way.
So you were just describing the quadratic arithmetic programs. I guess these are sometimes referred to as QAPs.
Right, exactly. Yeah.
Was this the predecessor? Was this the model that you kind of transformed or changed from? Or would you say you borrowed something from this research?
So there, I think basically I adopted that model, right? That's what I'm building on as well. I think as we become better at understanding and building zero knowledge proofs, there's emerged this paradigm, right? That you saw, you can take an arithmetic circuit, you take general computation, you can arithmetize it, right, and you can describe it as a set of constraints, and then you can build that into or convert that into a quadratic arithmetic program, and then you can prove things about quadratic arithmetic programs because, well, they're just polynomials and you can have polynomials in these secret exponents, right? So that's so like, I think on a very high level, the idea, right? And the idea is essentially it's goes back to the Schwartz-Sippel lemma, right? That you can check polynomial identities by just taking a random point and evaluating that, right? And then for the idea for these SNARKs is that, well, that random point can be built into the common reference string. And since it is an exponent and nobody can compute discrete logs, then nobody knows what is this point that you're evaluating in, right? So that prevents the proof from cheating.
You just mentioned the common reference string. This was actually going to be my question, is like, because I've always understood the paper as also transformative in terms of the trusted setup. And I'm wondering if this is where that link happens, where it's like using this sort of the way you constructed the common reference string allowed for a different trusted setup or not. Like, this is kind of actually a question to you.
So in the early literature on non-interactive zero-knowledge proofs, right? I mean, there was a bit of this discussion. I mean, a common reference string sometimes meant a uniformly random string, right? And when you do non-interactive zero-knowledge proofs based on trapdoor permutations, you just need that uniformly random string, right? And then, I mean, for these pairing-based SNARKs, you need some structure to the reference string. You basically need sort of ways to evaluate polynomials, so you need sort of powers of some secret value that you're evaluating these polynomials in, right? So it's really key to these trusted setups here that you have a particular type of structured common reference string which does not look uniformly random at all, right? Because it has embedded some very specific powers, right? And that also implies that you need somebody who constructs that trusted reference string, because if you just pick a random string, you're not going to get something which has these random powers.
Got it. And I guess then that also just like changed the way you did a trusted setup.
Right.
Like it altered what you needed to do in order to do it.
Right, yeah.
But there were trusted setups before, or was this the first time that like a SNARK introduces it?
So I guess there's always been a question of where do you get that common reference string, right? I mean, and the question of why should you trust that common reference string, right? So if it's a uniformly random reference string, though, you may try things as like, I will get it from some common physical source. I'll look at the sun, variations of sunspots and things like that. And maybe that could be used that, right? Or maybe I could just run a hash function, right? And it produces some outputs that look sort of random, right? And maybe I can use that, right? I mean, and the alternative to that is, okay, if you actually need a structure, you could think of using multi-party computation to do that. I mean, I also had a work that I did with Rafał Ostrowski where it was basically trying to sort of get something in between, right? So you say there are multiple parties that can contribute a common reference string, or in this case, it was a uniformly random reference string, right? But you don't have to trust any of them, right? But it was a little simpler model. You don't have to go through a multi-party computation. It's just every party who wants to contribute, they can say, here's my common reference string, right? And then when you want to prove something non-interactive, you can just collect some of these common reference strings, say, here's a proof with respect to this set of common reference string, right? And then if the verifier trust that, enough of these providers are honest, then you can believe the proof.
But so at what point was that MPC model of a trusted setup introduced?
That I don't actually know whether it's so like it. I think it's just been, for me, it's always been folklore, right? That well, if you need some common reference string and somebody has to set it up somehow, right? Multi-party computation would be a natural way to do it.
Yeah. But actually, this is the question: is like, was that the first time that was formalized? Like, I'm just curious if there had been work before using MPC as for a trusted setup, or if it was the Groth 16 paper.
So I don't think I want to take any credit for the combination of common reference strings and multi-party computation. I think it's never something I've really described in that step in my papers. I've just said, well, you can use multi-party computation, and then left other people to actually figure out how they would want to do that.
Understood.
Yeah, and I guess like you can see that result, in all the SNARK papers, it's very neatly abstracted away. You have this secret, and then you have complete other papers and huge amounts of code to do the actual multi-party computation. It's becomes quite complex.
This is something Kobe knows quite well. He's been our our local MPC trusted setup expert.
I have had to do a bunch of that. I think it speaks to one of the nice things of this era, which is that there's a lot of things that you really can compartmentalize into different disciplines, right? So a lot of the work I've done has been discrete logarithm groups or pairings. I'm not an expert on pairings and the underlying math of how you do that computation. Other people are experts in that, right? I wouldn't consider myself an expert in multi-party computation, but again, other people know that, and they can sort of build these common reference strings, right? And then, of course, there's all the implementation work. Again, I would not consider myself an expert of, how should you take a general piece of code and convert that into a quadratic arithmetic programs, right? But that's also something that people picked up. So I think it's actually really nice that you can sort of have these different fields of expertise, and you sort of have some nice interfaces between they can all work together.
Can we touch a bit on the Groth 16 paper itself? I think that the Groth 16 paper has kind of a misleading presentation in the sense that it's very low key. It's on the size of pairing-based, proof. It sounds, it sounds very humble, right? But it's actually quite a big result, and that became something that most deployments use today. Did you expect it to be that way? Did you expect it to be a big result?
I did not, right? I think, and the reason is that I'm thinking of this as a scientist, not as an engineer. I think this as, there was, so in some sense, when it comes to pairing-based SNARKs, I'm very happy with the paper I had in 2010 that first introduced this idea, right? And I thought that also for me, a big deal, right? Because it was something new, right? And then, Pinocchio really did a really good job of saying this is sort of right, getting really close to efficient, right? And I thought of this as an incremental piece of work that sort of took some of the ideas in Pinocchio and cleaned them up and squeezed things a little more together. And that gave you better efficiency and gave you more compact proofs. But I did not think of that as a big scientific step. I saw that as a sort of an incremental scientific step, right? And then I sort of matched it up with the lower bounds because I also want to understand, are we getting close to the limit of what we can do? And it still haunts me, this question of, is there something one can do in type 3 pairings that has 2 group elements? And I just don't know the answer to that question.
Can you also say something about the intuition of how the construction Groth 16 is made? Because maybe when you look at earlier papers like Pinocchio and PJHR 13, and it feels more compartmentalized, that you have here I'm proving knowledge, here I'm doing a check. But in Groth 16, everything is very much packed together and neatly organized. And, in the paper, you obviously present the final construction that works really well. So can you give something about the intuition?
Right. So actually, I think you already explained some of the intuition, right? Because part of what gives you the better performance is, Pinocchio is more cleanly structured and saying, this is what we're checking here, and that's what we're checking here, right? And I think it turns out that a lot of these things you can actually squeeze together. You basically work with polynomials. A lot of this is sort of engineering with polynomials and coming up with clever ways to sort of get everything together, right? So it's really about, designing some polynomials where you sort of check everything at once, right?
What was the impact of the paper once it came out? Was zCash the first team to implement it?
Okay, so this is actually really funny. It's the fastest implementation I've ever seen, right? So I put Groth 16 on ePrint. It was in the evening. I woke up the morning the next day. And I had an email from Alessandro Chiesa and Madar Virza, which said, we have implemented it, and these are the performance estimates that we have, right? So they really literally implemented it in a few hours, right?
Wow.
And I was like, wow, that's amazing, right? And of course, the reason they could do that is because they already had an enormous amount of tooling they had built. So it was basically they just needed to change some constraints in the description of those constraints, right? And then everything just showed that they had really an impressive tool chain for building zero-knowledge proofs. So yeah, that was super impressive.
But that implementation would have been still sort of like an academic implementation for testing, right? Like this was not industry grade.
Yeah.
So what?
That's the LibSNARK
This is
one.
LibSNARK. Yeah. Okay, interesting. And so what actually? I mean, at what point did you start to see it actually get used in production? And was there a lot of work that had to happen before that point, or was it pretty quick for people to start using it?
I think that went pretty quick, and it's probably zCash that's the first ones that did that. I was not very involved in that process, right? I mean, I was just this lucky academic that it turns out that I was in the field that people were starting to get interested in and adopting it, right? So I mean, in some sense, I'm really I think probably the opposite of the typical advice is, that as an academic, you have to do quite a lot of work to get people actually to be interested in your work and picking it up, right? And I was just like, I put out a paper, I could really lean back and now, and then somebody else said, look, this is great, we'll pick that up and use it, right?
Did this work come out before the first zCash? Sprout was the first one, right?
So zCash already had a different one, and I don't remember it was so like Pinocchio or it was some other version of sort of like similar complexity, right? So it was a later update where they said now we will switch and use Groth 16, right?
So maybe Sapling.
They added it in Sapling. Yeah,
and of course I was sort of like very happy to see that that it was getting out there and being used, and people liked the construction.
Yeah, by the way, it was also part of the kind of excuse to move to Sapling to hide the big bug they had.
Right, yeah. So they had, what was it, a group element too many in the common reference string that they should have not had.
Too many. And too many.
I see, okay.
And too many.
And too many, yeah.
But so that was potentially the first time, I mean, and we might be wrong here, but was at least the first kind of high profile implementation. But after that, I mean, it really became the standard for the industry.
Yeah.
Even now, I know that like work continues to be done on incorporating new things, tagging it into things. I mean, I think there's languages like, tell me if I'm wrong here, Kobe, but like languages like CIRCOM, which are like very much around Groth 16 and like how to interact with that particular proving system.
Yeah, exactly. And CIRCOM and you other huge deployments like Filecoin, and it's very much widely used, and it's implemented in pretty much every proving system implementations out there. So
right,
it's definitely very popular.
And I think that makes sense, right? I mean, it's also a question of, I think there's a lot of cross-contamination and help in setting on a standard, right? And being on the same page, and you can sort of get ideas from each other's implementations, right? So I think that's something you see quite often in that space.
Yeah, and it's really also really helps that that they've been for the most time extremely efficient compared to many other constructions. So in resource-constrained environments like the EVM, it was very useful to use Groth 16. Yeah. You could do it in like hundreds of thousands of gas, which is very reasonable.
I want to talk a little bit about what came after and some of the work that you would have continued on. As mentioned, we had Mary on the show just a few weeks ago talking about the work that she had done with you on trusted setup stuff, and then how that actually sort of opened up these ideas of universal SNARKs. After you published this paper, what kind of track were you exploring? What kind of direction? Were you looking to add incrementally to this particular direction, or were you looking at other problems?
Right. So I had a paper with Mary the year after, which thought about, can you add more stronger security properties to non-interactive zero-knowledge proofs, right? And so we had a paper where we had simulation extractable SNARKs. So again, based on pairings, it was again 3 group elements, right? But it gave you some extra security properties in terms of what an attacker can do. So it's not malleable. You cannot just change it, right? Whereas Groth 16 is re-randomizable. So that was sort of one piece of work under the hood, right? So there were the notions of quadratic span programs and quadratic arithmetic programs. That dates back to GDPR 13. But we've also sort of like along the way come up with square span programs and square arithmetic programs. Square span programs, that was an earlier paper I had with George Denises and Marcus Kohlweiss and Cedric Fournet. So that was like for Boolean circuits, right? And basically the idea is that, okay, so in a general span programs and quadratic arithmetic programs, you boil everything down to a couple of polynomials. Well, they're multiplied, they give some other polynomial. And the idea here is that instead of having a multiplication of polynomials, you have a squaring of polynomials. And that means that some of the group elements, the exponents of those group elements becomes the same. You can check that, and it sort of like puts an extra restriction of what you can do. So that's sort of like what prevents an attacker from, in the paper I have with Merit, from, mauling the proof, that you have that extra constraint, yeah.
But eventually it's actually not that restricting, right? Because you can quite naturally translate, let's say, the arithmetization or the work that you do in quadratic arithmetic programs to square arithmetic programs, yeah. Right? And so it's like a 2x factor or something of that sort, or 4x.
Exactly, yeah.
Yeah, and I think that exactly what you do in the paper with Mary, right? The SNARKs signatures.
Yeah. Yeah, so you change some things and how you do it. But I mean, it really is a sort of like standard math trick, right? That you can sort of like translate a multiplication into a couple of squaring and subtract those and so forth, right? So that's sort of like standard. And then it depends a little on the circuit, right? Or whatever initial statement you have, whether that's expensive or it comes cheap, that you can do that transformation.
Maybe one other thing about the paper with Mary. So the title for it is SNARKs signatures. So why signatures? That's, I think, would be interesting to discuss.
Yeah, right. Yeah, that's a good question, right? So this is this notion of signatures of knowledge, right? And this is something that dates back all the way back to Schnorr signatures, right? That you can think about those as being signatures and knowledge. In some sense, they're non-interactive proofs of knowledge, and it's like you're not just signing, but you're also in some sense proving that you know some underlying secret key, and that's sort of like the core idea, right? And this was essentially the same kind of thing we were trying to get to, right? It has the same properties as signatures of knowledge, but now it was pairing based, not based on hash functions in the future mere heuristic. So we thought that was an interesting connection to make, and that's sort of where it comes from.
What was some of the other work that you were doing around this time? And we should know, like Mary Maller was one of your PhD students, and also Jonathan Boodle, who's been on the study club, was also working with you at the time.
Yeah.
But yeah, what other work were you doing?
So another direction that we have been exploring is making interactive proofs more efficient, right? And I think at that time, so I had an ERC Stratton grant that gave me a lot of freedom to do research. Another direction was really trying to say, okay, what is the best prover complexity we can get, right? So because once you get down to sublinear complexity, I mean, the verifiers can be potentially super efficient. The verifier has to read the whole statement in principle, right? But if you have some encoding of the statement, then you can even have like a sublinear verifier complexity, right? And communication complexity can also be really small, right? And the remaining bottleneck is really on the prover side, right? I think that's what everybody struggles with. That it's expensive and it's expensive on many places in the pipeline, when you do the arithmetization and also when you do the proof itself, right? So, and whenever you do these kind of proofs based on cyclic groups, right, then you typically pay some exponentiations or something like that, right, to do the proofs. So one direction of research we looked into was, okay, right, what is really the best you could imagine from a prover perspective, right? The best you could hope for is really getting down to something that was more or less the same as if you just compute directly from the witness you have and the statement you have, right? I mean, so can you get down to something that is close to that. And we had a paper which was using error correcting codes and then some very efficient hash functions that gave really a constant overhead for the prover. And I think there's one thing I've always struggled a little with, right? So I think in the old days of zero knowledge proof, people would say polynomial time, right? That's efficient. You don't have to worry about, is it group operations or is it something else, right? And I think it really matters. What is the metric by which you are measuring the performance, right? It really makes a difference if it's like, is it, bit operations? Is it field operations? Is it exponentiations or group multiplication? All that has an impact on the performance, right? And there's a ton of papers that say, well, we can prove things in linear time for the prover, right? But what they mean is that it's linear number of field operations or linear number of group operations or something like that, right? And all of that is expensive, right? So what we got in this paper was that it was really a true constant, right? It was independent of the field size or the security parameter, right? So it really is. So you can prove arithmetic circuit satisfiability with a prover that takes does the same number of field operations, a linear number of field operations, right? So it really is a true constant overhead. It would compare to just having the witness and going through it and doing the computations. So that was like a really nice theoretical. I mean, in that paper, the construction is complex, right? And in practice, it would be a very large constant, right? But it was from a theoretical perspective, I think it was sort of like very satisfying to get that down to a true constant overhead for the prover. And we then had a follow-up paper also where we looked at sort of concretely if you wanted to do computation based on, say, tiny RAM, right? Then what would be the overhead, and there was actually a little bit more overhead because there you sort of like you don't do it in the field size is bigger than the unit size of the elements you're operating on in tiny RAM, but depending on what that gap is, right, you can also get very close in performance.
I want to kind of go back to this work that led to the universal SNARKs. Like, I understand that you were very involved in that as it was kind of being produced, but it wasn't like, and stop me if I'm wrong here, but it wasn't really coming out of your lab. It wasn't necessarily like your initial work, but rather you were brought in on this work, right?
Right, yeah.
And this is the work that led to Sonics, and I guess one can say down the line led to Marlin and led to Planck. What was kind of exciting about that for you? And what was sort of your take and contribution? What did you kind of add to that?
Right, yeah. So that was, it was an interesting way it came about. So Mary was my student. She was working with Markov at Microsoft. I think it was Microsoft that sponsored her PhD. So she came back with this interesting problem, right? I mean, well, maybe you can do something more general about the common reference strings. Maybe it can be updated and then things would be fine. I don't remember if they did not have a construction or they had a very cumbersome construction anyway. But it was interesting because it was all like also taking me back to the 2010 SNARK, right? Because that SNARK was based on monomials in the exponents, and instead of having a more structured setup where you actually have polynomials. And it turns out that monomials you can re-randomize. So like I knew exactly the right thing, and I could dig back in my memory and say, oh, there's some ideas here I can use to do that, right? So it was actually something, and it really took me, I think, a long weekend or something like that to sort of like get sort of like the main structure up and running, right? And then trying to optimize again and getting down to as few group elements as possible. So, but ideas when you've worked in a long time in a field, right? There's a lot of ideas running around in your brain, and sometimes you can sort of like go back in that pool and fish up, and it may be used in a different context, right? So I think few people other than me had sort of like thought much about that, because at that point you had Groth 16 and so forth, right? And people would probably just jump to that straight away rather than think back. But well, since I had that old paper, I also knew about that, right? And I could sort of like take those ideas back and use that. And they had exactly this advantage, right? That it was universal, right? In terms of the circuit you could use as opposed to being specific to a circuit, right? So it also sort of like ties back that loop.
Just to touch, but I think that we talked about it with Mary, that work specifically was not practical to use, right? Because it was quadratic in the size of the common reference string, right?
Right, yeah. So the first paper, right, it was... So basically, you have the universal common reference string. You have to construct this specific common reference string, right? And there was sort of like a matrix multiplication in the exponents that you had to do. I think that was expensive.
Right. Yeah, I think it would be interesting to move to DFINITY, because there's also some interesting work there.
Yeah, let's do it. So you're currently the Director of Research and Formal Security at DFINITY. Talk to us a little bit about that move. And do you get to do ZK stuff at DFINITY? That's my real question.
Right, yeah. So the move was basically, I thought it would be exciting to do something else. I had sort of like just wrapped up a big grant, and my students were graduating. So it was also a place where I could sort of like do a natural move without harming anybody in the process. I joined DFINITY. I knew Jan Kamenisch from before. And my PhD student, Andrea Chiruli, had also just joined DFINITY. So it was also like that through him that the connection was established. And as I think all the academics that have joined DFINITY, right, you sort of like start out with, taking a leave of absence from the university. So you can always come back later on if it doesn't work out. But I think we've all stayed at DFINITY. so in general, it works out pretty well.
So what kind of work do you do? Do you get to do ZK stuff? I guess that's the real question.
Yeah, so I have not actually done that much work on zero knowledge in DFINITY. So one piece of work I did was designing our non-interactive distributed key generation protocol. We have a sharded blockchain, right? So there's a bunch of shards, or we call them subnets, right? Where you have nodes and they have a secret key, right? And they do threshold signatures on behalf of the shard whenever something is updated about the state. So you can sort of like just verify that signature and see that it's the right thing you have. And the question is, okay, when you have a new node that's being replaced or something like that, right? Or also maybe for proactive security, you want to update like those shares that the servers hold once in a while. So there we use a non-interactive distributed key generation protocol. And it's nice that it's non-interactive. It sort of like makes the logic easier behind the process, right? So the idea is that you have a share, so like that describes how the secret for this threshold signature that we're using. And you want to be able to, so like each node has a share of that secret, right? They want to contribute a resharing of that secret, right? So a new set of nodes, maybe the old set of nodes, or maybe set where some of the nodes have been replaced, can sort of like pick up and get a new refreshed share of the secret key. And there's a bit of zero knowledge proofs in that. There's also so a lot of optimization again. So it's sort of like a multi-encryption scheme that sort of like encrypts multiple parties at the same time, and you still want to have chosen ciphertext attack security. So there's a lot of thinking going into that as well. And zero knowledge proofs are used to basically prove that they are doing the right thing in that operation. And it is a SNARK. It's sort of like, but it's a hand-tailored SNARK to this specific problem, right? So it's sort of like optimized for exactly this use case, right? So it's kind of thing again, because of my background, it was so like
you had to put a little in
for me to do that, right?
Yeah.
So I was happy to get that into the protocol.
I have a question, Kobe. This because you just did some DKG work as well. Is it related? Do you see any sort of similarities in this?
So I think that maybe there are some overlapping motivations in the sense that you want this non-interactivity, which is really useful, and it simplifies handling a lot of failure cases, and parties can go offline, online, and it's really nice to have this verifiable encryption part. But what I think is really interesting about Jens's work here is that it's done for field elements, which, you had some prior works around that with Fuchs-Stern and others, but this one really pushed the boundaries in optimizing it. And the work, for example, that Mary and I've been doing with the group back then was for group elements. So in some sense, you are very strongly then deciding what kind of signature schemes you can use. So with field elements, you can still use ECDSA signatures and Schnorr signatures, but with group elements, you are now restricted maybe to producing, random beacons or some new signature scheme like the one that we had in that paper. So one of the most recent work you published was around this asynchronous ECDSA signing service. What can you share about it?
Yeah, so there's been some interesting questions there. So this is work with Victor Schub, who's also working at DFINITY, and he's sort of like the lead on this project. So like have been helping him in that. So the motivation is that we want to integrate the internet computer with Bitcoin. So basically, you can sort of like send Bitcoin to an address on the Bitcoin network. It gets picked up by the internet computer. You can do things with it on the internet computer, and maybe later on you want to send Bitcoin to somebody else, and the internet computer can sort of send Bitcoin directly on the Bitcoin network. So we're very excited about that. So DFINITY is the foundation that's building the internet computer, right? And the internet computer is a decentralized blockchain. The idea is that people can use the internet computer to build smart contracts applications on the internet computer. That should be a very easy process. It should be very performant. It is super performant, right? And it also has on-chain web, so you can sort of like serve web directly from the blockchain or from the smart contracts. So that's something we're also very excited about.
Got it. And bringing it back to what you just described. So you're talking about bringing Bitcoin into this environment.
Exactly, right? So the idea is that you can send Bitcoin to an address that sort of like is accessible by the internet computer. So every smart contract, so you have key derivation with respect to ECDSA signatures. That's a BIP32 standard, right? So you can actually every smart contract for every smart contract you can derive a Bitcoin address on the internet computer. And if you send Bitcoin to that one and tell the internet computer, hey, I sent some Bitcoin, right? Then the internet computer can pick up that Bitcoin. It may later on send Bitcoin again to different addresses on the Bitcoin network. And then on the internet computer, you can imagine then having wrapped Bitcoin, and basically you could build DEXs and things like that for using Bitcoin. So I think it's very exciting integration, right? Because you can basically build smart contracts now on the internet computer that has all the sort of like the nice interfaces on the internet computer, the web, and so forth, right? That and you can use those applications to send and receive Bitcoin.
In this work, this was one of the first work that we have in ECDSA signing, which works in an asynchronous model. So what's like unique and important about that?
Yeah, so I think there's been a lot of interest in threshold ECDSA signatures, and exactly because then you can do Bitcoin transactions and other types of transactions. We specifically opted for the asynchronous model because we think that's the most realistic model. I mean, that is the internet and things can't get lost and not arrive at the destination, right? So we think that's sort of like the right conceptual model. And so that's sort of going stepping back in the process, right? We wanted to do an integration with Bitcoin. For that, we wanted to be able to threshold sign ECDSA signatures. And then stepping back, we started looking at sort of like the protocols for threshold ECDSA. And there's actually quite a lot of work that had not been done. So one thing we published at Eurocrypt this year was a security analysis of ECDSA itself, right? To just look at those properties that people have been used, right? So one property, for instance, is that people have used is you can sort of like there's a random element you first compute and then you sort of like do some other steps in the ECDSA signing process. And people have suggested, well, instead of computing that element after you see the message, why don't you pre-compute that, right? And just make it public for everybody, and then you can use that, okay? But that's not actually been analyzed in very carefully in the literature, right? So there are people using these ideas that have not been analyzed that carefully. I mean, there is another work that sort of analyzes that. And then we had some ideas there as well. So you may actually take that public element, but if you re-randomize before you use it with a message, then you actually get stronger security guarantees. I think there was some nice analysis going all the way back to ECDSA that we encountered in that process.
Very cool. I think we're pretty much at the end of the interview, but is there anything that people should look out for, something like future work that they should keep their eyes open for?
Then I guess we have a lot of things going on at DFINITY for the internet computer, right? So we're also looking into sort of like advanced DAOs, so then that will allow applications to do tokenization and have decentralized governance, and you can on-chain vote and decide on upgrades to the protocol and so forth. So there's a lot of like really nice functionality working on. Sort of like more up my alley, perhaps, so like the crypto-specific things, right? So some things that we're interested in looking into the future is sort of multi-party computation for confidentiality of data and post-quantum security.
Cool.
So we look out for Groth 23, I guess.
Groth 23.
Yeah.
Fine. I'm sorry.
Jens, thank you so much for coming on the show and sharing with us your journey, talking about some of these really important works in our space. And I'm very excited to see what's next.
Yeah, thank you. And thank you, Kobe. It's been a real pleasure to be here.
Thank you.
So I want to say a big thank you to the Zero Knowledge Podcast production team, Henrik, Tanya, and Chris, and to our listeners. Thanks for listening.